Hello students. So let us continue with the exercise of alcohol, phenol and ether. So we have done till 14 questions in the previous class. Now let us move to the 15th question. The 15th question says, explain why is orthonitrophenol more acidic than orthomethoxyphenol. For that, let us first draw the structure of this orthonitrophenol. So orthonitrophenol would look like this. So first we have phenol here, and at ortho position we have a nitro group. So this is orthonitrophenol. Similarly, we can have methoxyphenol, and that is also at ortho position. So these are the two structures whose acidity are to be compared. So if I ask you that which one will show the minus I effect and the minus I effect and minus M effect, so that will be NO2. So it is an electron withdrawing group. Okay, this is an electron withdrawing group, and hence it will help in removing the H from here. Okay, now if I talk about this OMe, then it is increasing the electron density through lone pair donation. So this will make the abstraction of this hydrogen difficult. Okay, is this clear? Now next thing you have to notice here is that once this gets deprotonated, okay, once this gets deprotonated in this way, you will get a O negative charge here, right? And this O negative charge is stabilized, right? This is again stabilized by resonance. Okay, you can see that this bond will go here, this will go here, this will go here, and at last it will be moved on to O minus. So it is stabilizing the formed, or you can say the conjugate base, and plus it helps in removing the H plus. So due to this reason, this one is more acidic. So the structure that will be formed is this one. Okay, NO minus, yes, and plus. This is O. Clear? So this is the structure. Now next, what can we do? So if you just want, you can just make this in this fashion also. Okay, so this is the stabilization of the negative charge that is being formed on the oxygen. Now due to this reason, the acidic character of the nitrophenol is more than the methoxyphenol. Now let us look at the solution. See, the nitro group is an electron withdrawing group. The presence of this group in the ortho position decreases the electron density in the OH bond. As a result, it is easier to lose a proton. Also, the orthonitropenoxide ion formed after the loss of proton is stabilized by your resonance, as I have shown. Hence, orthonitrophenol is stronger acid. Where on the other hand, the methoxy group is an electron releasing group. Thus, it increases the electron density in the OH bond, and hence the proton cannot be given out easily. So what is being said here is that, so suppose we have the structure of methoxyphenol. So this is methoxyphenol. Now, what is required to break the bond here? Why I'm saying that electron donating and electron releasing group are important? So basically what you have to do, you have to pull this bond. Okay, you have to cut this bond or cleave this bond. For that reason, there should be an electron withdrawing group that is attracting this bonded pair towards the oxygen. But if you just see this thing, then you can clearly see that after resonance, there is a development of negative charge on the same position. On this position, right? Through your plus M effect. Through your plus M effect, a negative charge develops here. Now electron density is increasing on this position because of the OMe group. Clear? So due to this reason, it is difficult to now extract this proton. Next question. Explain how does the OH group attached to a carbon of benzene ring activate it towards electrophilic substitution. So how does it does so? So you know very well that this electrophilic substitution means we are adding a substance, or we are adding a species which are attracted towards electron. Now, if in any way, if you are increasing the electron density in the benzene ring, then that would help in increasing the rate of electrophilic substitution. Now, the thing is very simple here. So if you just look at the OH group, it looks like this on the benzene. Now, it donates electron in the ring through what? Through the plus M effect. Okay. Now, due to this simple reason, the electron density increases in this benzene, and hence electrophilic substitution becomes easier. The OH group is an electron donating group, as I have told you, and thus it increases the electron density as shown in the structure of the phenol. So you can see here how the electron density is being increased. Okay. Now it is more reactive towards electrophilic substitution. Next question. Give equation of the following reaction. First is oxidation of propane-1-ol with alkaline KMnO4. So what happens on oxidation of propane-1-ol with alkaline KMnO4? It oxidizes to your carboxylic acid. What happens? KMnO4, what it does? It oxidizes. It is strong reducing oxidizing agent. Hence it oxidizes alcohol to your carboxylic acid. So this is propane-1-ol. CH3. Okay. So if we just treat it with alkaline KMnO4, then it completely oxidizes it into carboxylic acid. Next question. Bromine with CS2 phenol. Okay, bromine with CS2 phenol. So if you treat bromine water, if you treat phenol with bromine water, then it results in tri-substituted. But in the place of that, if you use CS2, okay, if you use CS2, since it is a non-polar solvent, okay, since it is a non-polar solvent, the structure of CS2 looks like this. The polarity is cancelled out. So since it is a non-polar solvent, therefore, the electrophilic aromatic substitution becomes difficult. Because you know now, if you see the intermediates that are formed during electrophilic aromatic substitution, they all are ionic in nature. So to stabilize the ionic intermediate, you will need a solvent that is having some dipole movement. But here, no dipole movement is present in the solvent as compared to H2O. So if you use H2O, that is a polar solvent. Okay, so that will stabilize the intermediate that is formed during electrophilic aromatic substitution. But since CS2 is non-polar in nature, it will not stabilize it, and hence bromination will be inhibited. Therefore, it will result in ortho and para substitution. It will result in ortho and para substitution. Clear? Next is dilute HNO3 with phenol. So again, nitration will occur and ortho and para substituted product will be given. Treating phenol with chloroform in the presence of aqueous NaOH. So what it is said here? So we have phenol and phenol with chloroform. Chloroform formula is CH3Cl3 plus aqueous NaOH. How it will go on? So this is a name reaction, right? This is a name reaction in which we treat our phenol, with aqueous NaOH and chloroform. Okay, aqueous NaOH and chloroform. So what will be the reaction? So the reaction will be resulted in the formation of salicylaldehyde, and this is called as Remer-Timmer reaction. What is called? It is known as Remer-Timmer reaction. Okay. So this is salicylaldehyde. So since we are not protonating it, so in the first step it will result in O minus Na plus just. Now if it was again treated with say H plus and H2O, then it will result in protonation of this O minus group. So see, first one is propanoic acid, second one is orthopara, third one is also orthopara, and fourth one is this one. So what they have done, they have treated it further with H plus. So if H plus was given, then we would write this product. If it is not given, then we leave it to this phenoxide ion. After that, we have to explain this following reaction. So this is just a simple theoretical question. We will see, okay, how it will happen. First one is Kolbe's reaction. So in Kolbe's reaction, the phenol is treated with sodium hydroxide to form sodium phenoxide, and upon treatment of that your O minus, the formed O minus, that phenoxide ion, if you treat it with carbon dioxide, then it results in the formation of carboxylic acid. Okay, so how it goes? So initially you will have this thing. Okay, you treat it with a base. Suppose I am treating with aqueous NaOH, then it will result in O minus and Na plus. Now further, if you just simply treat it with CO2, then this will happen. We'll draw the mechanism. This will go down and it will attack this carbon dioxide. Okay. Here it will bond. Here it will be CO, O minus, double bond O. Clear? So this is it. Here we have hydrogen also. Now next what will happen? We'll just protonate this thing. Okay. So this will go up and result in this kind of species. So first this will be protonated and then this will be protonated. So that would result in OH and CHO here. So as you can see, we have just treated with H plus further to protonate and get salicylic acid. So it is salicylic acid and not salicylaldehyde. Okay. Next is Reamer-Timmer reaction. We have seen it just now. Treat it with CH3 and aqueous NaOH and then further protonate it to give it this salicylaldehyde. Next we have Reamer-Timmer. After Reamer-Timmer we have Williamson synthesis. Okay, in Williamson synthesis what do? We take alkyl halide and treat it with the alkoxide ion. Now this lone pair on O attacks on R and removes this X. This results in ether. And it is generally used to prepare symmetrical and unsymmetrical ether. So if R and R dash are same, then it will result in symmetrical. And if R and R dash are different, then that will result in unsymmetrical. And it is simply following this SN2 reaction. So if we have a secondary and tertiary alcohol, then that would give us low reaction. Okay, so this is very important. And I think in case of tertiary halide, it gives an elimination product rather than a substitution product. Okay, so if the alkyl halide is secondary and tertiary, then elimination competes over substitution. So this is very important. You can use only primary alkyl halide here and no other alkyl halide other than primary. Okay, so in case of unsymmetrical ether, suppose we are taking this step up to form this. So we'll take CH3, CH3, CH2, O, Na plus CH3X. So why I am taking this as CH3X and this part as CH3ONA? Because it is a SN2 reaction, and since if we take CH3, CH2, it will be more hindered. So I have taken CH3 and attacked this. Write the mechanism of the acid dehydration of ethanol to ethene. So let us see how it can happen. What we have to do, we have to do acid dehydration of ethanol. So this is ethanol. Here is CH3. Here is CH2. We have to do the acid dehydration. So first, we will protonate this O, okay, with the help of H plus, as the condition is acidic. So H here, and OH2. That is a positive sign. Now next, what will happen? Next, since it's an acid catalyzed reaction, we will get our H plus back. Okay, we will get our H plus back. So H plus will be released in this step. And we get a alkene. That is our ethene. The first step is protonation. Okay. Second step is what? Second step is elimination. That results in ethene. Okay. Next question. How are the following conversion carried out? First is propene and results into propane 2-ol. Propene results to propane 2-ol. So this is propene. This is propene. So what we will do, we will simply treat it with H plus H2O. Okay, H plus and H2O. So that would result in. So what we have to do, we have to form propane 2-ol. Okay, we have to form propane 2-ol. So is this clear? So how it would have taken place? First of all, protonation would have taken place, right? So after protonation, we will get this thing, H with a positive sign. This H will go here such that it results in a positive sign on secondary carbon, because secondary carbocation are more stable. Okay. Next, what will happen? This H2O will attack in this position. O H2 with a positive sign. Okay. In last step, what will happen? This H here on the OH2 will be deprotonated. And H plus will be removed. That will result in alcohol and sec 2 degree alcohol. Next is benzyl chloride to benzyl alcohol. So what we have? We have benzyl chloride. So this is benzyl chloride. How will form benzyl alcohol? Just simply treat it with aqueous NaOH. Okay, treat it with aqueous NaOH. It will directly give your product through SN2 mechanism. Ethyl magnesium chloride to propane 1-ol. First, write the structure of ethyl magnesium chloride. And what we have to form? We have to form propane 1-ol. Propane 1-ol. Here is 3H and here is 2H and here is 2H. So this we have to form. We have to increase one carbon. How we'll do it? We'll simply treat it with HCHO. That is our formaldehyde. Okay. Now this will give a SN2 reaction. It will go here and will result in this thing. Now further we will just protonate this thing to get our final product. Methyl magnesium bromide to 2-methyl propanol. Methyl magnesium chloride to 2-methyl propanol. So at 2 position we have methyl, and at 2 position we have alcohol. So how we will do it? For that we will take this thing. So suppose we have CH3 here. So we need this thing. Okay, so we'll treat it with CH3, and this guy will attack here. It will move here. And O negative will be formed. Okay. After that, we will just protonate it to get our final product. See, so they have done the protonation first and resulted in the formation of propan-2-ol in the presence of H2O. In this thing, we have treated with NaOH, so they have done it right. We have done it right. Again, they have protonated it and got our benzyl alcohol. Third one is this one. Okay, so this is the third one. So we treat it with formaldehyde and later protonate it with H2O to get our final product. And here also we have taken a ketone and treated it with magnesium bromide, methyl magnesium bromide, and further we have just protonated it. Next question. Name the reagent used in the following reaction. Okay, name the reagent used in the following reaction. First is oxidation of primary alcohol to carboxylic acid. So we have seen this. Okay, we can use KMnO4 directly. Okay, we can use alkaline KMnO4. What else can we use? We can use H2Cr2O7. That is our Jones reagent. Okay, so this two we can use. Oxidation of primary alkyl to aldehyde. Okay, so for that we can simply use CrO3. Okay, that will convert your primary alkyl to aldehyde only. Bromination of phenol to 2,4,6-tribromophenol. So it is Br2H2O. Because our phenol is very rich in electron density due to the donation of electron from the oxygen. So that increases the rate of electrophilic aromatic substitution, and hence we get a tri-substituted phenol. Next we have benzyl alcohol to benzoic acid. Again we can use our carboxylic acid. Sorry, we can use our alkaline KMnO4. Okay. Then dehydration of propan-2-1-ol to propene. So for that we can use copper at a higher temperature, that is 573 Kelvin. Butane 2-on to butane 2-ol. So this is what? This is reduction. Okay, this is reduction. You can use LiLH4. Okay, we can use LiLH4, that will reduce your ketone to alcohol. Okay. So first is acidified potassium permanganate, as I said. This is pyridinium chlorochromate. Next is, so in place of CrO3 we can also use this pyridinium chlorochromate. Next one is bromine water, as I said. Then again acidified potassium permanganate. For dehydration they have used 85% phosphoric acid. So we can use Cu also. And for the last we have LiLH4 or NaBH4. Give reason for the higher boiling point of ethanol in comparison to methoxymethane. So ethanol, if you see, so ethanol has the hydrogen bonding advantage, whereas in methoxymethane we do not have any such case. They have only some polarity, so that due to that polarity they have some dipole-dipole interaction. That's it. But in case of ethanol we have hydrogen bonding also. So ethanol undergoes intermolecular hydrogen bonding due to presence of OH group, resulting in the association of molecule. Extra energy is required to break this hydrogen bond. On the other hand, methoxymethane does not undergo hydrogen bonding. So you can see here very clearly the hydrogen bonding is being formed between the oxygen of one alcohol and the hydrogen of other alcohol. Clear? In this, we have to write the IUPAC name. So we will take the shorter one first. So which is the shorter alkyl group? It is this one. Then we will name it as ethoxy. Okay, ethoxy. Then what is being left? We are left with this part. So it is propane, 2-methyl propane. Ethoxy 2-methyl propane. Next is what? Next is methoxy for this group and 2-chloro what? 2-chloro ethane. What about this? So this is what? This is methoxy. Methoxy. So this NO2 is at para position. Okay. So para nitro benzene. So it is being mentioned here. It is para. Methoxy para nitro benzene. And this is methoxypropane. What about this? So this is ethoxy. 1, 2, 3, 4. 4,4-dimethyl cyclohexane. Next, again we have ethoxy benzene. So 1 ethoxy benzene, 2-chloromethoxyethane, 4-nitroanisole. So they have written the common name. I was giving the IUPAC name. Then we have 1-methoxypropane, 4-ethoxy-1,1-dimethyl cyclohexane. Okay. So what they have done is they've given the methyl group first numbering. Okay, so this we have done wrong. So it was like this. So this one is given first priority, second, third, and fourth. At fourth position, we have ethoxy. Okay, at fourth position, they have ethoxy. Then we have given this, right? Next is ethoxy benzene. Question number 24. So we have to write the names of reagents and equation for the preparation of the following ethers by Williamson synthesis. First is 1-propoxypropane. Okay, 1-propoxypropane. So 1-propoxypropane would look like this. C3. Okay, C3H437, C3H7O, and again here we have also C3H7O. Here is ethoxy benzene, C2H5O, and then benzene. 2-methoxy 2-methylpropane. Okay, 2-methoxy 2-methylpropane. So suppose we have a propane here. So at 2 position we have methyl group, and at 2 position we have again methoxy group. It is 1-methoxyethane, so that will look like this. And next what we have to do? We have to write the name of the reagent and equation. So we don't have to give the structure. We have to write the names of reagents, okay, and equation for the preparation of the following ether. Okay, so how we'll do it? So for this case, we will take the phenoxide ion, that is C3H7, C3H7O minus Na plus, and treat it with C3H7. Suppose I am taking here chloride. So this will just kick this out and result in the final product. See, they have used bromide, you can use chloride also. For ethoxybenzene, what we will take? For ethoxybenzene, we will take C2H5. Okay, C2H5X bromide, suppose, and what? it is treated with phenoxide ion. Next is 2-methoxy-2-methylpropane. So this one. So for that, I have told you, you cannot do the attack on secondary alcohol. Okay. You cannot do the attack on secondary alkyl halide. That would result in elimination. So we'll use this as the alkoxide ion, O minus Na plus, and treat it with CH3Br. What about this? So we'll use CH3Br plus T2H5O minus and Na plus. Okay, clear? This is also taken as this. Next we have this here. Okay, now question number 27. So in this you have to illustrate the example of the limitation of Williamson thesis. So I have told you, so if we are using a secondary or tertiary alkyl halide, then that will result in elimination product rather than substitution product. So here you can see, okay, so they have used this thing. Okay, now in the place of this, if we use in such a way, suppose we have used in this fashion, right? Here is the Br and here is CH3O minus Na plus. Now since it is already a tertiary carbon, so this negative charge will abstract a proton from here and Br will release and an alkene bond will be formed. So for that reason, we take this one as the alkoxide ion and not this one. Clear? See, a double bond is formed. Next question. How is 1-propoxy propane synthesized from propane 1-ol? Write the mechanism of that. So what we have to what we have to form? We have to synthesize 1-propoxy propane. So at one position we have propoxy from propane 1-ol. Propane 1-ol. So what we can do is we can take 2 moles of this. Okay, we can take 2 moles of this. Further, in the next step, one of the mole you should treat it with a base that would result in alkoxide ion, and the other one you should treat it with what? Substitution product. Sorry, nucleophile that would substitute your OH with your alkyl halide, right? So if you have to convert CH3, CH2, CH2OH into CH3, CH2, CH2Br. Okay, so what will take? How can we convert it? So we have to do this, right? What can be done here? So you can simply use SOCl2. Okay, treat it with SOCl2 and that would result in chloride. You can use chloride also as the alkyl halide, and one of the mole is treated with base. So if you treat it with base, then that would result in CH3, CH2, CH2, ONA. So they have taken 2 moles and they have just done it. Okay, so we have shown that how we'll convert first. Okay, so first we'll convert one of the mole into, say, our alkyl halide and another mole into alkoxide ion, and then we'll perform the reaction. So you can use it in this way also. Just treat it with H plus and H2O. So this will protonate this over here. Okay, and once it is protonated, the other mole will attack here and that would result in this thing. And at last we'll just deprotonate it. Next question. Preparation of ethers by acid dehydration of secondary or tertiary alcohol is not a suitable method. Preparation of ether by acid dehydration of secondary and tertiary alcohol is not a suitable method. Again, the same reason is here. The formation of ether is followed by SN2 mechanism. In the method, alkyl group should be unhindered. So if you take an unhindered, so that would result in elimination product. Next, write the equation of the reaction of hydrogen iodide with propoxypropane. Okay, so you have to treat hydrogen iodide with propoxypropane. What will happen? So first, it will be protonated, your propoxy. So this is our propoxypropane. So this will be protonated first. Okay, and this group will leave along with a positive sign. So since it is a positive sign, it will be leaved here. And this will contain the positive sign. That is the carbocation. Okay. See? And the I minus will attack on this part, which is the carbocation, and this will result in 1-idopropane. Similarly, if you treat this one with HI, so this thing will form. Here also, I will be formed and CH3, C2OH5O will be leaved.